Here we have one of our first example problems where we'll be looking for the eigenvalues and eigenvectors of the matrix shown here. And one of the things I'd like to point out is that it is a symmetric matrix across the diagonal defined by 1, 1. That symmetry means that we can be assured of real eigenvalues, and it also means that the eigenvectors we're going to find are going to be perpendicular or orthogonal. So that's just one of the curiosities as we start. I'm going to add an extra component to this problem, and that is that once I find my eigenvalues and eigenvectors, I'm going to check to make sure that my solution is correct. So we start off by calculating the determinant where we take lambda off each of the diagonal terms. So we set that determinant equal to 0, which means when we expand this, we get 1 minus lambda squared minus 9 equals 0, which we can expand to 1 minus 2 lambda plus lambda squared minus 9 and set that equal to 0, or I can rewrite this as lambda squared minus 2 lambda minus 8 equals 0. I can factor this by inspection, but if you need to use the quadratic equation, you're welcome to. You will need to memorize it if you plan to use it, because you won't have an equation sheet for exam 1. But I can factor this with lambda minus 4 times lambda plus 2. And the roots then are four and minus 2. These are the eigenvalues. But now we need to find the associated eigenvectors. To do this, we're going to need to go back to our original matrix, and now we're going to have to subtract the eigenvalues off each diagonal term and solve a system of equations. So I'll need some room. So we'll start out 4 the first eigenvalue, lambda equals 4, we will set up the system of equations that's defined by 1 minus lambda. We don't take anything off the non-diagonal terms, and the other diagonal term was 1 minus lambda x1, x2 form an x vector that will be the terms of our eigenvector, and we set that equal to 0. And we plug in the value of lambda equals 4 and solve for the x1 and x2 that are going to make this work. So that means we're going to get an augmented matrix of 1 minus 4 minus 3 minus 3, 0, minus 3, 1 minus 4 minus 3, 0. We're going to have a solution in no time. We use Gaussian elimination. And all this is saying is that 3 minus 3x1 is equal to 3x2, or x1 is equal to minus x2. We arbitrarily pick the last one to be 1, just to be systematic. You don't need to make that choice, but I encourage you to, so your answers will always look like mine. But if we select x2 as 1 then that tells us that x1 is going to be minus 1, and this is the evec, or the eigenvector, for lambda equals 4. Now we also have to find the eigenvector for lambda equals minus 2. And in that case, we're going to be taking minus 2, subtracting minus 2 from each of the diagonal terms. So we again have 1 minus lambda, minus 3, 0, minus 3, 1 minus lambda. That's our system of equations that we need to solve. And when we plug in a value of lambda equals minus 2, we end up with 3 minus 3, 0, minus 3, 1 minus a negative 2 or positive 3, 0, which through Gaussian elimination we can see we get 3 minus 3, 0, or x1 is equal to x2, and that suggests an eigenvector of that's the eigenvector for lambda equals minus 2. I always make it very clear what the association is, because for every eigenvector we have a distinct associated eigenvalue. I always make that very clear. I mentioned that we were going to check to make sure that we indeed have the correct eigenvalues and eigenvectors, and we can do that by taking the original matrix and multiplying it by each of the identified eigenvectors to demonstrate that what we get as a result is the eigenvalue times the original vector. So for the original matrix, if we multiply it by the eigenvector 1, 1, we get 1 minus 3 minus 3 plus 1, that's equal to minus 2 minus 2, which we can factor out the minus 2. This shows us that our lambda is equal to minus 2, and we have the original eigenvector back. So in fact, we've demonstrated that indeed 1, 1 is an eigenvector, and the eigenvalue associated with it is minus 2. Now let's check our other result, and that is we can take the original matrix and multiply it by the other eigenvector that we found above, and look at that result, and we get minus 1 minus 3 and 3 plus 1, which is equal to minus 4 and 4, which is indeed equal to 4 times this eigenvector, telling us that the associated eigenvalue is 4. So we've proved that we indeed solved the problem correctly. That's a very useful thing to be able to do, is to prove that you found the correct answer to the problem that we were setting out to solve.